So in Chapter 9, we address both translational and rotational motions. And so how do we describe the two types of motion using both principles? So we have the momentum principle and also the energy principle. So in the momentum principle, we say that the total momentum is the product of the total mass and the velocity of the center of mass, and that's equivalent to taking the sum of the total momentum. And the total kinetic energy is equal to, by taking the sum of the translational kinetic energy and the rotational kinetic energy. And that's equal to half times m times the velocity of the center of mass squared plus half times the moment of inertia of the system times omega squared, which is the angular speed. And that's also equivalent to taking the sum of the total kinetic energies. So let's apply this and solve this problem. So we have, in this case, a solid sphere of mass 10 kg rolling across a horizontal floor without slipping. Without slipping meaning that it grips the floor, and there is a combination of translational motion and rotational motion. So when it encounters a ramp, which is tilted at 30 degrees, with respect to the horizontal, it starts to move up the ramp. So the first part, let's determine the translational kinetic motion, the translational kinetic energy as it reaches the base of the incline. So we can calculate the translational kinetic energy, and that's equal to half times the mass and the square of the velocity of the center of mass. And that's half with a mass of 10 kilograms. And at the base of the ramp, it has a velocity of 5 meters per second. So we square that, and we get an answer of 125 joules. So the translational kinetic energy is equal to 125 joules at the base of the ramp. The second part of the problem wants us to calculate the rotational kinetic energy of the sphere as it reaches the base of the incline. So we know that the rotational kinetic energy is half times the moment of inertia and the square of the angular speed. So for a sphere, we have the moment of inertia of 2 over 5 times the mass and the square of the radius of the sphere. So that makes the rotational kinetic energy to be equal to half 2 over 5 times the mass and the square of the radius and the square of the angular speed. And since we know that the velocity of the center of mass, and that's equal to the radius times the angular speed, and that gives us 1 over 5 times the mass and the square of the velocity, and we plug in the values, and that gives us a rotational kinetic energy of 50 joules. So in the third part of the problem, we have the same sphere rolling without sliding, but now it's rolling from the base of the incline onto the ramp. So if the sphere rolls without sliding, so meaning that there is rotational motion and translational motion determine how far up the ramp it has rolled when it stops. So that is finding the distance it has traveled up the ramp. So we need to find the distance L traveled up the ramp, but the ramp it goes out to a height h above the floor. And so meaning that from geometry we have h over L, and that's equal to sine 30 degrees. So we can use the energy principle to solve this problem. So initially, when the sphere is at the bottom of the ramp, it has an initial translational kinetic energy of 125 joules. But when it goes up the ramp and stops, we have a final translation kinetic energy of 0. And likewise, when it goes up the ramp and it stops, it also has a final rotational kinetic energy of 0. But when it is at the base of the ramp, the potential energy at the base is 0. But when it has gone up the ramp to a certain distance, height of h above the horizontal, we have a final potential energy of m, g, and h. So now we can write the energy principle where delta E, the changing energy of the system, which is conserved, and that's delta K, translational, plus delta K, rotational, plus delta K, delta U, gravitational, and that's equal to 0. So that we know now the change in translational kinetic energy, which is that of the final minus the initial, gives us a negative 125 joules, and that of the rotational kinetic energy, right, which is the final minus the initial, gives us a negative 50 joules plus m times g times h, and that's equal to 0. So now we have m times g, where h is L sine 30 degrees, and that's equal to 175 joules. Since m times g times L sine 30 is equal to 175 joules, therefore the length up the slope, that's equal to 175 divided by the mass times g times sine 30 degrees, and that gives us a final value of 3.57 meters. So let us answer the last part of the question, which is that suppose in C the ramp is frictionless. There's no friction with the sphere going up the ramp, and this implies that the sphere cannot roll. So as it cannot grip the surface, it's unable to roll, so there's no rotational kinetic energy. And so in this case, determine how far up the ramp the sphere has traveled. So without friction, the sphere is unable to roll, so therefore there's only translational motion going up the ramp. And therefore the change in the gravitational potential energy is the negative of the change of the translational kinetic energy. And that's equal to 125 joules. So we know as before that the change in gravitational potential energy is m times g times the height above the surface, and that's L sine 30. And that gives us L, the distance up the ramp, that's equal to 125 divided by mg times sine times 30 degrees, and that gives us a final value of 202.55 meters. So we can see that without friction, that the sphere rolls at a distance up the ramp far less than if there is friction.